In this segment, we'll talk about the Halpin Tsai equations for the elastic modular unidirectional lamina. So we'll look at how is E1, E2, nu12, and G12 calculated by using the Halpin Tsai equations. So the Halpin Tsai equations for E1 and nu12 are exactly the same as the mechanics of materials approach. So we don't have to worry about recalculating those two elastic moduli. Now, the reason why we do need different formulas, or there was a need for different formulas for E2 and G12, was because when they compared the experimental results for E2 as a function of volume fraction, they found out that the experimental results were very far away from the mechanics of materials approach. And the same thing was for when they looked at G12 versus VF, that the mechanics of materials approach, which is this line right here, is far off from the experimental results which they get for the same composite material. So that's why there's a need to see that, hey, how can we get different formulas for G12 and E2? Again, recognize that, hey, these are the rule of mixtures, and the formulas for which we have trouble making the experimental results and the theoretical results to be similar to each other is for the two formulas which have the inverse rule of mixtures formula. So we've got to figure out what G12 and EU2 are based on the Halpin Tsai equations. And what Halpin and Tsai did was they said that, hey, let's go and make a three-dimensional model and see that how we can develop some empirical formulas for G12 and E2. Because if you use the 3D models, they are quite complicated in nature. It requires a solution of nonlinear equations and so on and so forth. So what they wanted to do was to come up with some simple formulas for G12 and E2 based on what they got for the 3D model, and be able to backtrack it to a simpler formula for G12 and E2. So let's take an example here. This is the formula which they came up for E2. So all you need is, in order to calculate E2 by using the Halpin Tsai equations, you need the Young's modulus of the matrix, you need the fiber volume fraction, of course, and then you have these two new parameters coming in, xi and neta. However, neta is based on some kind of a ratio of the fiber Young's modulus to the matrix Young's modulus right here, and you have xi right here. So in fact, you have only one unknown, which is xi right here, because if you know xi, you can calculate neta, and then you'll be able to use this particular formula. What is this xi dependent on? It is called something called the reinforcing factor. It depends on three things: fiber geometry, is it circular in shape, square fibers, rectangular fibers, and so on and so forth. Packing geometry is that, hey, how are they packed? Are they packed in a square shape? Are they packed in, let's suppose, in a rectangular shape? Are they packed in some kind of a hexagonal shape? So you have all of these different possibilities of how the fibers are packed, and it will depend on that also. And then the loading conditions, so we'll see an example of that in a little bit. Loading condition is that, hey, are we loading it, let's suppose, are we trying to find the properties which are, let's suppose, when you are loading in this direction or when you're loading this direction? That'll make a difference, maybe not for the square packing of fibers, but surely for the rectangular packing of the fibers, because if you're loading it this way, then it may mean something different. If you're loading it this way, it may mean something different in terms of what the value of xi will be. A good example is for a fiber geometry of circular fibers in a packing geometry of square array, which is this one right here. Xi is given as 2 for E2. So you can take that and use that for the value of xi for circular fibers in a square array. Now people say that, hey, how do they come up with these formulas? They have come up with these formulas with some recognition for some theoretical basis. So you can call these formulas to be semi-empirical in nature, because they're not totally coming out as empirical formulas from your exact or your 3D models. So for example, if your if fiber is same as the matrix, then you will get EF by EM equal to 1, right? EF by EM will be equal to 1. If no, EF by EM is equal to 1, then EF by EM is 1, and then this numerator will be 1 minus 1 will be 0, so you'll get neta equal to 0. Now, if EF by EM is infinity, that means the fiber is much more rigid than the matrix. Then you can say EF by EM approaches infinity. In that case, what's going to happen is that neta is going to approach 1. How do you get that? Neta approaching 1 is that, hey, if you divide by EF by EM on both sides, you get 1 minus 1 divided by EF by EM divided by 1 plus xi divided by EF by EM, and when EF by EM approaches infinity, you will get simply 1 as the limiting value. And what does that mean? That means that you have rigid inclusions. EF by EM equal to 1 means that you have homogeneous medium, that the fiber and the matrix are the same. Now you have EF by EM equal to 0, that means that you have voids, that there is, instead of fibers, you have nothing there. And in that case, what you're going to get is neta is equal to minus 1 by xi, which is right here, that this is 0 and this is 0, so you get minus 1 divided by xi. So those are the 3 limiting cases which you're seeing here. So there is some method to this madness in terms of how they picked up these particular formulas for xi and neta. Let's go and see how we can apply it to an example. Oh, before we do that, let's see xi for another case. We talked about that the xi term, which is the reinforcing factor, depends on fiber geometry and packing geometry and loading conditions. In the earlier example, we said, oh, if there are circular fibers in a square geometry, we get xi equal to 2 for E2. But hey, what does this mean, loading conditions? So in the loading conditions, this is a good example of loading conditions. Xi is 2a divided by b. So if you have rectangular fibers and they are, let's suppose, in a hexagonal array, so you have rectangular fibers in a hexagonal array, then xi is 2a divided by b, where a is the length and b is the width, where a is in the direction of the loading. Because let's suppose if you're trying to find E2, you're going to apply load like this, right? So this side here is in the direction. This side here is in the direction of loading. So that's what we call as A, and the other direction we call as B. Now, if I was applying a load like this, I wanted to apply sigma 3 so as to find E3. Then in that particular case, my A and B will get interchanged because the loading is in the direction B. So the loading is in the direction this one. So A and B will get interchanged in that case. So that's what we mean by, hey, this xi is dependent on fiber geometry, packing geometry, and loading conditions. That's what we mean by the loading conditions in this particular case. So let's look at an example here. We have transverse Young's modulus here. For a glass epoxy lamina with 70% fiber volume fraction, we're getting the values of the properties from table 3.1 and 2, and we want to use the Halpin Tsai equations for circular fibers in a square array. So if it's a circular fiber in a square array, that means our xi is 2. Young's modulus of the fiber is 85 gigapascals. Young's modulus of matrix is 3.4 gigapascals. So let's go and use this particular relationship first, because that gives us the value of neta. So we have EF, EM, all these values which are here, and that gives us the value of neta equal to 0.8889. Now we apply it back into this formula right here, which is the ratio between the Young's modulus in direction 2 divided by the matrix Young's modulus. So that's 3.4 GPa, 1, xi is 2, neta is 0.8889, volume fraction is 0.7, same thing here. And that gives us a Young's modulus of 20.2 in the direction perpendicular to the fibers. Now look at this. This is your Halpin Tsai equation, this one. That's your Halpin Tsai equation. This is your mechanics of materials approach. And these are your experimental data points. You can see that how close the experimental data points are to the Halpin Tsai equation. This figure and this figure are exactly the same. The only difference is that we are plotting them for a smaller range of fiber volume fractions right here. And then again, it amplifies that how good the Halpin Tsai equations are working. You got, this is the mechanics of materials approach, this curve, And this curve is the Halpin Tsai equations, and then the circles which you see all around here are the experimental data points. It still has issues at certain fiber volume fractions, but it is better than what you are getting for your mechanics of materials approach. So that's what we get for the transverse Young's modulus for comparing mechanics of materials approach versus the Halpin Tsai equations. In the in-plane shear modulus, we have the same thing. The formulas are similar. The only difference is that you have now the ratio between G12 and GM. Xi is still called the reinforcing factor. Depends on the fiber geometry, packing geometry, and loading conditions, just like we talked about. However, for G12, Xi is not 2, Xi is 1. So it all comes from the 3D model which they developed. So it's not anything which they are just picking out of the hat. But the Xi value turns out to be 1 if you have circular fibers in a square array. Now let's look at, because we talked about the fiber geometry of circular fibers in a square array, hey, what does it mean loading conditions? So loading conditions are very clear here. If you have a rectangular fiber cross section, you'll have the 2 dimensions of length and width, right? And then the Xi is given by this formula for G12, square root of 3 log A by B, different from for E2. And A is in the direction of loading, so A is in the direction of loading. So if we are trying to find G12, then A is this direction, or this side, which is this side right here, and B is the opposite side. If we were trying to find G31, for example, then we will have the A and B reversed. So that's where these loading conditions part comes from. So once we have done that, let's go and look at an example. We're asking to use Halpin Tsai equation to calculate the shear modulus of a glass epoxy composite with 70% fiber volume fraction. Properties are given in table 3.1 and 2. And we are assuming that the fiber is circular and packed in a square array. If they are circular and packed in a square array, Xi is 1, because for G12, Xi is 1 for this particular reinforcing factor here. The Young's modulus of the fiber, the shear modulus of the fiber and the shear modulus of the matrix was calculated when we do the mechanics of materials approach, so we don't need to go through those steps. Then we can calculate the neta from the formula, and then the G12 from the other formula. So once we have that, we get neta equal to 0.9288. We substitute that 9288 value here and here in order to calculate what G12 is. So that's how you use the Halpin Tsai equations. Again, if you are looking at the comparison between the experimental data points and the Halpin Tsai equations and the mechanics of materials approach, you're finding out this is the mechanics of materials approach, this is the Halpin Tsai equation, these are the experimental data points, and they're very close to each other. And if I choose a smaller range of the fiber volume fractions in order to amplify the difference between the experimental results, the Halpin Tsai results, and the mechanics of materials approach, you're seeing this is the mechanics of materials approach, this is the Halpin Tsai equations, and the experimental data points are very close to the Halpin Tsai equation than the mechanics of materials approach right there. And that's the end of this segment.